All right, good afternoon, everyone. Welcome back for the final talk of today. Before doing so, I'd like to encourage everyone again to submit talks to the lightning session on Friday. It's going to be low-key, and you can present open problems. We built up this sort of shared language over the course of a week. So if you'd like to present open problems or quickly talk about things that are bothering you, please submit ideas. But with that, we're going to hear about bounds on LDPC codes from Nouédyn.
Hi. Yeah, this talk is going to be about bounds on LDPC codes. And before talking about the bounds, I'm going to talk about what are stabilizer codes. So imagine you have like, can everyone see? Okay. Imagine you have like a bunch of qubits, and one of these qubits might be corrupted by an error here in red. And one thing that you can quite naturally do is you're going to perform some measurements on your qubits in the hope that one of these measurements is going to identify this error so that you can correct it later. Oh, shit. I'm so sorry. Okay, this is going to be annoying. Great. So, right. These measurements are going to define both your code and its properties. We're interested in mainly 3 properties: n, the number of qubits that you have in your system; k, the number of qubits that are protected by the noise; and d is the size of the smallest error that you cannot detect. Given that different codes are going to involve different measurements, you're going to end up with different connectivity structures with your qubits. So like here, for example, you have like the very famous 2D surface code, and here you have the also famous 3D Turing code. And these different dimensions are directly related to the fact that the logical operators are also going to change shapes. So yeah, it's like the famous string operators for the 2D surface code, and like the 3D Turing code is going to have a different structure. Now, unfortunately, these codes in low dimensions, they don't perform very well. We have bounds called the Bravais-Poulin-Tahoe bounds that you've heard about today before. And it might be like the first time that you're seeing these equations in their full generality, and it's okay if you don't, if you're not familiar with them. The point is mostly that you have a bound on the distance that gets less restrictive as the dimension d increases. And similarly, you have a trade-off between k and d that gets less restrictive as the dimension d increases as well. Yes, great. So the fact that these bounds exist kind of suggests some natural questions. What is so bad about low-dimensional codes? In some sense, it's kind of obvious that it's about the connectivity, but in what sense precisely? How do we generalize these spaces to non-Euclidean spaces? Similarly, you can ask the question from the other point of view, where we have lots of good codes now, thanks to recent advances. It's not entirely clear what makes them so good. We have heard of like expansion a lot. To what extent expansion is that necessary? What makes a good code a good code? Right, so in this talk, I'm going to, yeah, so the aim of this talk is going to talk about how we can quantify connectivity, and secondly, how from this quantification of connectivity alone, we're going to be able to obtain bounds on quantum codes. In the context of this talk, we're going to use a few different metrics. The first one is going to be the separation profile, and the other one is going to be expansion that we've heard of before. To define these metrics, I'm going to, because they're graph theoretical metrics, I'm going to need to introduce a graph associated to a code. And the kind of graph that we're going to use is called the connectivity graph. This is the surface code, and this is the associated connectivity graph. You have one node per qubit, and you have an edge between 2 nodes if they are involved in the same measurements. Okay, so now I can tell you about the separation profile. I'm so sorry about this. Great. So some graphs have a particularly uniform structure. What I mean by that, if you look at a 2D lattice, you can remove essentially square root of n vertices and separate it into two parts that are approximately equal. If I zoomed in into another area, then I would have the same property where I can remove square root of n vertices to separate it into two approximately equally sized regions. And I can do that again and again and again. And this property of these graphs is called being S-separable, where S is the function that tells you how many vertices you need to remove in function of the size of the subgraph. So, for example, in the case of a 2D lattice, the function S would be square root of the size of the subgraph. Great. We're going to be particularly interested in cases where the function S is a polynomial. So you can bound it by a polynomial. And there has been a series of results using this metric. The first one was in 2021, and we obtained this bound on the distance and similarly a trade-off between K and D. And recently we improved this result to the same bound on the distance, but a tighter trade-off between K and D. This might be the first time that using these separation profile-based bounds, so I'm going to try to give you a picture of what they look like. So when you apply these bounds to codes that live in 2D, these are the bounds that you get. So the Bravitel bound is definitely the tightest one. We still don't get the first bound is very much not as strict, and the more recent bound gets you half of the way there. So the sense that we have is we did better, okay, but we're still not quite optimal. And I'm going to try to explain to you how we got to these bounds. So the first notion that I'm going to use is that of a correctable region. You might have heard of it during this workshop. A region is said to be correctable if, I forgot to put a figure here, but imagine that you have your bunch of qubits and you lose a set U of your qubits. This set is said to be correctable if there is a recovery operation R, such that even if I'm left with everything that wasn't in U, I can recover it. I can recover the original state that I had before I lost my qubits. Something that's quite interesting about a correctable region is that I can actually compose them. So out of smaller correctable regions, I can make bigger ones. The first lemma that we're going to use is the union lemma. It says that if I have two regions, it's here you have U and U prime, and if they're far enough from each other, namely if they are disjoint in the graph, then if they are disjoint in the graph and each region is correctable, then the union is correctable. The second lemma we're going to use is kind of a complement of that. It says that if you have a region T that is correctable, and then you have a region U that contains the boundary of T. So the boundary is the set of all nodes that have an edge going into T. So if U contains the boundary of T, and U is also correctable, then T and U is correctable simultaneously. Great. The last thing we're going to use is this extremely useful fact discovered by Bravitel and Tahal that says that if I can partition my qubits into three sets such that A is correctable and B is correctable, then I can bound the number of logical qubits encoded by the code as the size of the remaining region C. So now to build these bounds, it kind of becomes a game of how do I build the biggest correctable region I can. And I'm going to walk you through how the original BPT paper does that. So the idea, you start by assuming that you have a relatively large distance, because any set that is of size less than the distance is correctable. So you assume that the single qubit is correctable. Then you can use the union lemma to show that all of these, that the union of all of these, because they're far enough from each other, then they're also correctable. And then I can use the expansion lemma. If I assume that this boundary is smaller than D, I can grow these regions until Well, until I get to the point where these boundaries have size d. So what does that give me? One way to capture how well the partitioning is to see how many vertices are now in the first correctable region. And here you can calculate it, the complement of A, so A is like the big red region here. The complement of A scales as n over d. Now, how do we obtain the B region? Because each of these boundaries has size roughly d, it's quite straightforward to see that you can take out these regions that scale as d. They're each correctable because you can take them to be smaller than d. And they're also disjoint in the graph, so their union is correctable. And you obtain your region B. And eventually, the region C is going to be whatever remains, which in this case is just a single qubit there. When you scale up and you have like more regions like these, this is the kind of partitioning you get and the size of C, so the maximum number of logical qubits that you can encode, scales as n over d squared. Great, now I'm going to walk you through how we can port this argument to a geometry oblivious context where we only use the separator. So imagine that you're taking a separator out of your graph, and then you can recursively separate your graph until all of these regions there that remained have size smaller than d. And because of the property of the separator, they're all disjoint, and they are all correctable because they're all size smaller than d. So you can use the union lemma and show that the complement of this blue region here is correctable. We can ask the same question of like, okay, how good is this partition? Well, it's not as good as the first method because we get a complement of A that scales as n over square root of d instead. And the reason for that is that we didn't use the expansion lemma. So like each of these regions there is going to scale roughly as d instead of scaling as d squared. Now, how do we obtain the region C? We do kind of the same thing where we recursively separate the complement, like the blue region here, and until each of these blue regions has size d, and they're all separated. And so we get a union of regions that is correctable, and we obtain our C region. And C scales as n over d instead of scaling as n over d squared. And in our recent work, we managed to improve this partitioning, and the main insight was figuring out how to use this expansion lemma to obtain bigger regions that are correctable, and so having a tighter bound on the number of logical qubits. And here's how it goes. So imagine that you have a region that has a relatively small boundary. So like this boundary here, we're going to assume that it scales as d. And furthermore, we're going to assume that this region here can be big, but it has to still be small enough such that when I take a separator out of it, the separator has to be smaller than d. So what I can do now is like I can recursively separate it as before, and I do that until the regions I get are all of size d, so the union is correctable and everything. But that's not what we want to do. We want to show that this whole region there is correctable. One good first step would be to show that this little patch here is correctable. And the way we're going to do that is by using the expansion lemma. How? So these two regions are separated. They're also smaller than d, so they're both correctable, but we're still missing the region that is in between these two bits. So the way we're going to solve that is to use the expansion lemma. And for that, we need to show that the boundary, which is like this darker green region here, is also correctable. How do we do that? Well, this boundary here is contained within the union of this separator and this separator and this separator, basically in the union of the separators that come in the levels before, and the union of this boundary there, the original boundary of D. And we can show that the sum of all of these vertices scales as the separator of G, and by assumption, this was more than D. So we have shown that this region here in like dark green is correctable, and therefore the whole patch is correctable. Now what we can do is repeat this method again and again to bubble up through the graph and show that this is correctable, this is correctable, this is correctable, this is correctable, and on again, until we come back up to the whole subgraph, and we have shown that the whole subgraph is correctable. Great. How do we use this method in a general partitioning context? So we start the same way. We take out a separator, and we recursively separate the graph until instead these regions, not that they have size d, but instead the separator scales as z. Once we have that, we can show actually that most of these regions there that are remaining also have boundary scaling as d, which is what we want. However, a few of them are still going to have a big region. So like you can look at this region there, and it's like not, it has like a relatively big boundary compared to the rest of, compared to its size. So what we can do is recursively separate this specific region until it is made up of small regions of size z. So because we have done that, this region is correctable. The other regions that have a small boundary are also correctable by using the previous lemma I mentioned. And we do obtain a partitioning that has a really good, that is quite optimal. So like the union of this, this blue region and this orange region also scales as n over d, which is exactly the same thing that we had in the BPT context. So that's great. That's amazing. Now it remains to find the C region. We do the same thing. We separate the blue region over and over again. Sorry. Until we get correctable regions that are disjoint. And what we get is something that is better than what we had before, but it's still not the BPT bound. And as a summary, we have like the BPT bound. Sorry. We have the BPT bound is optimal, but not general. We have the previous result that is general, but not optimal. And we have this new result that is kind of better, but still not entirely optimal. The main bottleneck is once we get to that step, the graph that we have to separate is kind of very tree-like in a way. And so the separator of this remaining graph, we expect it to be much smaller. The problem is that capturing how small it gets after this first separation step is kind of tricky, and we haven't really found a way to do that. One solution is to use a different graph metric to recover BPT, and this is some future work. We have some ideas about how to use a different metric that actually recover BPT while remaining geometry oblivious. And on a related subject, I'm going to now tell you about graph expansion. Great, so for those of you that are not familiar with expansion, the idea is like in a graph, you can look at how big the boundary is. So like if you look at a region U here, you can look at how big this boundary is relative to the size of the region U. So here it's captured by the ratio of the boundary of U over its size. And we want to capture how well connected the graph is. So we're going to minimize over all the sets U. And G is said to be epsilon expander if this metric there is bigger than epsilon. And the way I think about it is that the expansion is kind of a converse to the separation profile. So for example, if I look at this graph here, what the separation profile tells me is that this graph is easily separable. I can remove this vertex here, and then I have two subgraphs of equal size. The expansion tells me the opposite. It tells me that if I look at a graph, then there's no way for me to separate it easily. What I'm going to use next is we want to capture how well not just the graph is expanding, but also all its subgraphs of a certain size. So like I want to look at all the subgraphs of size at least m, and I want to calculate how expanding that subgraph is. Once I know that, imagine that I have a graph here such that it's this quantity is small for a certain m. It kind of means that this graph is made up of a bunch of bundles of size m, but like the connection between these bundles is kind of bad. What I can do now is quite naturally separate it into these little clusters, and then I get a nice partitioning. So like you can do some graph theory stuff, and eventually you get that if this quantity is upbounded by that quantity, then you get a separation of your graph such that into regions of size m by using at most epsilon n vertices. So like at the boundaries there, you have at most epsilon n vertices. Great, and so now we can use that in the same context. We can do, okay, we have like a separation theorem.
Can I ask a question?
Yeah.
If you do all subgraphs, that includes a line. And the line you can cut very easily, so you don't
Yeah. Okay, so like this is the so this is the maximum over these.
I see.
Yeah. Great. So great. And so now what you can do is like, okay, I have my partitioning theorem. I can use it. I can obtain a BPT-like bound, and indeed that's what we do. Now, why do we care about that? We already have the BPT bound. We already have bounds that rely on connectivity alone. But there are two things that I want to tell you about. So the first is that this bound is tighter in other ways, and I'll come back to it. The other one is like, if I focus on expansion, it gets a lot easier to obtain converses of these bounds. If I tell you that a graph actually has a certain amount of expansion, then maybe I can use this expansion to build a good code. Right. Okay. So I'm going to talk about like in the ways that it is tighter. So by using the separator bounds, I can show that if you give me a good code, then its connectivity graph is going to necessarily contain expander graphs. And the reason why it's bad is because like if I try to take my connectivity graph and embed it into my architecture, then the presence of those expander graphs is going to be an obstruction to that. So you can see that if you have an NKD code, then you have like a bunch of subsets such that the size scales as delta times k. H is relatively large, delta times d, where these subgraphs are somewhat expanding for a certain delta that scales as most as k over n. It's actually like a lot smaller than that, but I just want to give you an idea of what that statement looks like. What we can do by using bounds on expanders is that this statement becomes a lot stronger, actually. You can, instead of having all these things corrupted by this little factor delta here, you just actually get something that's much nicer. So the sum of these subsets is actually of size k at least, and each of these is actually of size d. And they're each at least square root of k over n expander. Great. Now I'm going to touch back on the converse part. So there has been lots of works recently on like how to take a non-local code and massage it into a local architecture. And a natural question is, if I have an architecture that's not entirely expanding, but it has some amount of expansion, can I do that? Can I take a non-local code and massage it into a local architecture? Part of this intuition is backed up by the fact that expander graphs are really good at embedding other graphs. So you can like route a bunch of paths in them in a really nice way and everything. So like this is like a reasonably good intuition. And so we have results that show that this holds in the case of classical codes. So for classical codes, you kind of have like now this almost converse, where if you give me an NKD classical codes, I can tell you that its connectivity graph has to contain some amount of expansion. And conversely, if you give me an expander graph, then I can show you that I can embed a classical code with these parameters in this connectivity graph. It's not tight yet. The target that we would like is to have a better encoding rate and a better distance. But it's quite notable that we can take like an arbitrary architecture and then have some kind of guarantee on the codes that we can embed. To my knowledge, this is like the first result of this kind. And it would be really interesting to know if this can be expanded to quantum codes. And I think, yeah, can this be generalized to quantum codes? I think that's it. Thank you.
We have lots of time for questions.
At the beginning, you showed the scaling with expansion coefficients. Can you show them again? Are these results at the very start of the talk, I think second or third slide, which looked like generalization of
I think
T.
this.
Yep.
Yeah.
Right. Okay, and can you tell this and also where are the references?
Oh, yes, I must have forgotten. So like they're in the graph right there. So yeah, so like the less tight bound is our work with Annie, and the tighter bound is with Venkat, Annie, and Rayleigh. Yeah. Sorry about that.
Any other questions? All right. Well, let's thank Nouédyn again.